Well, welcome back to our class on discrete mathematics, looking at a focus on computer science with discrete structures. We are now at the last lecture for a lot of the information that we've covered from Rosen. And so this should be an interesting chapter. A few parts will get a little bit technical, and so I'll try and keep it at a high level. But we'll go in and have some fun reviewing this information as we now figure out how we go about modeling computation and how that has been done over quite some time. So the first thing that we're going to get into is looking at modeling computation. We'll look at languages and grammars, finite state machines with outputs, finite state machines with no outputs, language recognition, and Turing machines. And so that's the synopsis of the whole chapter. So computers can perform many tasks. Given a task, two questions arise. The first is, can it be carried out using a computer? Once we know that first question, then with an affirmative answer, we can ask the second question is how the task can be carried out. Models of computation are used to help answer these questions. So we're just beginning to get the tools to how to be doing programming effectively. And there's a multi-layer process to do that. And I hope that you all have an enjoyable time taking those steps going forward. So we will study three types of structures used in models of computation, namely grammars, finite state machines, and Turing machines. Grammars are used to generate the words of a language and to determine whether a word is in a language. Formal languages, which are generated by grammars, provide models both for natural language, such as English, and for programming languages, such as Pascal, Fortran, Prolog, C, and Java. In particular, grammars are extremely important in construction and theory of compilers. The grammars that we discuss were first used by the American linguist Chomsky in the 1950s. Various types of finite state machines are used in modeling. All finite state machines have a set of states, including a starting state, an input alphabet, and a transition function that assigns a next state to every pair of a state and an input. The states of a finite state machine give it limited memory capabilities. Some finite state machines produce an output symbol for each transition. These machines can be used to model many kinds of machines, including vending machines, delay machines, binary adders, and language recognizers. We'll also study finite state machines that have no output but do have final states. Such machines are extensively used in language recognition. The strings that are recognized are those that take the starting state to a final state. The concept of grammars and finite state machines can be tied together. We will characterize those sets that are recognized by finite state machines and show that these are precisely the sets that are generated by a certain type of grammar. Finally, we'll introduce the concept of Turing machine. We will show how Turing machines can be used to recognize sets. We will also show how Turing machines can be used to compute number theoretic functions. We will discuss the Church-Turing thesis, which states that every effective computation can be carried out using a Turing machine. We'll explain how Turing machines can be used to study the difficulty of solving certain classes of problems. In particular, we will describe how Turing machines are used to classify problems as tractable versus intractable and solvable versus unsolvable. So that's just a little bit of a starting point for us to think about. So let's think about languages and grammars to begin with. So we'll talk about phrase structure grammars, type of phase structure grammars, derivation trees, and Backus-Naur form. Words in the English language can be combined in various ways. The grammar of English tells us whether a combination of words is a valid sentence. For example, the frog writes neatly is a valid sentence because it is it's formed from a noun phrase, the frog, made up of the article and the noun frog, followed by a verb phrase. Writes neatly, made up of a verb write and an adverb neatly. We do not care that this is a nonsensical statement. In that sense, we are just concerned with only the syntax. So syntax is one of the things that we want to be thinking about, or the form of the sentence, and not its semantics, which is the other thing, looking at the meaning that we want to be thinking about. We also note that the combination of words swim quickly mathematics is not a valid sentence because it does not follow the rules of English grammar. We'll see that in a chart or two, so we'll come back to that. The syntax of a natural language that in a spoken language such as English, French, German, or Spanish is extremely complicated. In fact, it does not seem possible to specify all the rules of syntax for a natural language. Research in the automatic translation of one language to another has led to the concept of formal language, which, unlike a natural language, is specified by a well-defined set of rules of syntax. Rules of syntax are important not only in linguistics, the study of natural language, but also in the study of programming languages. We also described the sentences of a formal language is using a grammar. The use of grammar helps when we consider the two classes of problems that arise most frequently in applications to programming language. One, how can we determine whether a combination of words is a valid sentence in a formal language? And two, how can we generate the valid sentences of a formal language? So I mentioned this, but now we can see it in a chart. Syntax versus semantics. Semantics is a form, semantics is the meaning. And so we had this first one I mentioned, the frog writes neatly. It follows the right syntax, but it doesn't mean anything. The sequence of words swims quickly mathematics is not a valid sentence according to the rules of English grammar. And so thus we can be thinking about these two things we want to think about. The rules that specify the syntax correctly, syntactically correct sentences of a natural language such as English are complex. Instead of studying natural languages, we can define formal languages that have well-defined rules of syntax. These rules of syntax are important both in linguistics, which is the study of natural languages, and the study of programming languages. So here's an example of a grammar. I won't walk through this. There's a lot of details here, but I'll refer you to Rosen to digest this in more details. You can have a phrase structure grammar where you have a vocabulary that is an alphabet, a word, or a sentence over V is a string of finite length of elements of V. So you have symbols that are used in the vocabulary, and those form words, and those words form sentences. The empty string or null string denoted by lambda is a string containing no symbols. The set of all words over V is denoted by V star. A language over V is a subset of V star. The elements of V that cannot be replaced by other symbols are called terminals. For example, the a, the, and rabbit in the example grammar. Those that can be replaced by other symbols are called non-terminals. For example, sentence, noun, phrases, etc. So the rules that specify when we can replace a string V star with another strings are called productions of the grammar. So those are just some things to be thinking about here. A phrase structure grammar with this G equals VTSP consists of vocabulary, a subset T of V consisting of terminal symbols, a start symbol S from V, and a finite set of production P. In terms of derivations, let G equals VTSP be the phrase structure grammar. Let W0 equals LZ0R, that is a concatenation of LZ0 and R, and W1 be LZ1R, be the string over V. If Z0 then Z1 is a production of G, then we say that W1 is directly derivable from W0 and write W0 then W1. So this is just some more information about derivation that you can go ahead and review an example. I'm going to skip over that example. Well, what about language generation? This is one of the things that we would want to be doing with computational abilities. So let G equals VTSP be a phrase-based grammar. The language generated by G, denoted by LG, is a set of all strings or terminals that are derivable from the starting state S. So this just gives us some more information about how we can go about thinking of language generation. I'm not going to read all of this, but continue to be thinking through this, these details. So what about the types of phrase structure grammars? And so here we have 4 different types, 0 through 3. And so the phrase structure grammars are classified by the types of allowable productions. So no restrictions, and then we get into more and more restrictions. Type 2 grammars are called context-free grammars. A language generated by a context-free grammar is called a context-free language. Type 3 grammars are called context-sensitive grammars or regular grammar. A language generated by a context-sensitive grammar is called a context-sensitive language or regular language. So those are some more things to think about. We can have derivation trees. So we can represent the derivation of the language generated by a context-free grammar or by an ordered root tree called a derivation or a parse tree. And so this might be a helpful diagram for you to get some perspective. And you have a sentence, you break that down that you have to have a noun phrase and a verb phrase. And then you can have various things that you can add to that. So the hungry rabbit eats quickly. And so the rabbit eats is the most fundamental thing. And then you can have some other things that help to make this more readable. And so that's an example of how we can be thinking about a derivation tree. The Bacchus null form is sometimes used to specify a type 2 grammar. It is often used to specify the syntactic rules of computer languages. The productions of type 2 grammars have a single non-terminal symbol on the left-hand side. All the productions with the same non-terminal symbols on the left-hand side are combined into one statement using the symbol that we have here instead of the arrow designation. Additionally, all non-terminal symbols are included in brackets, and the right-hand side of the productions are separated by bars. So you can see the syntax there if you'd like to follow that in more detail. In the programming language Algol 60, an identifier consists of a string of alphanumeric characters and must begin with a letter. So the BNF, Bacchus NAR form, descriptors of allowable identifiers is listed like that. So that's just an example. I'm not going to get into Algol 60 discussion in detail. All right, let's move on. Let's think about finite state machines with outputs. That's the first type that we'll look at. And so many kinds of machines, including components and computers, can be modeled using a structure called a finite state machine. So several types of machines are commonly used in models. All these versions of finite state machines include a finite set of states and a designated starting state, an input alphabet, a transition function that assigns a next state to every state, and an input pair. Finite state machines are used extensively in applications in computer science and data networking. For example, finite state machines are the basis for programs for spell checking, grammar checking, indexing or searching large bodies of text, recognizing speech, transforming text using markup languages such as XML and HTML, and network protocols that specify how computers communicate. In this section, we will study those finite state machines that produce output. We will show how finite state machines can be used to model a vending machine, a machine that delays input, a machine that adds integers, and a machine that determines whether a bit string contains a specified pattern. So many kinds of machines, including computers, can be modeled using a structure called a finite state machine. And so we got a chance to be thinking about that already. A finite machine consists of a finite set of states, designated start state, input alphabet transition function, and assign a next state to every state pair. And as we'll see a little bit later, some types of finite state machines produce outputs. That's what we're focusing on for this section. Finite state machines have many diverse applications, as I mentioned, including XML, HTML, but any other things, spell checking, grammar checking, etc. So here is an example of a finite state machine with output. So this is a vending machine, accepts nickels, dimes, and quarters. When 30 cents or more has been deposited, the machine returns the amount over 30 cents. And so the customer can then press an orange button to receive a container of orange juice or a red button to receive a container of apple juice. So those are the things that you can get, orange juice or apple juice. And then you're going to get some change depending on what you put in. So this just gives you an idea. The output is the orange juice, the apple juice, and possibly some change. So this is how we can be representing the finite state machine. And I'm not going to go through this. This is actually gets complicated here. But you can see that even with a simple machine, there's a lot of connectivity that we have to be leveraging. And so some of the graph theory that we've introduced, we get a chance to be seeing that pictorially, and that's going to help us to get our head around it and figure out how we're going to design this to make this work. So here is some more details on finite state machines with outputs. And so a finite state machine, M, has S, I, O, F, Q, and S0, consisting of S states, a finite alphabet, a finite output alphabet, transition functions that assign to each state, and a input pair a new state, an output function G that assigns to each state, an input pair an output, and an initial state S0. So here we can see a table that's trying to gives us a synopsis of what that would be. And so that's what we have there for putting that all together. A unit delay machine is an example of something that is important in electronic devices, which produces an output. As output, the input string delayed by a specific time. And so it pads with an initial strings of zeros. So it's a delay line, a programmable delay line, if that makes sense to you. So this just gives you another example of something we can be looking at. We can also construct a finite state machine that adds two positive integers. And so this just gives you some details about this, and we have another illustration of what that would look like. Okay, now let's talk about finite state machines with no outputs. So we can think of the set of strings, finite state automata, language recognition by finite state machines, designing finite state machine automata, and finally non-deterministic finite state machine automata. So one of the most important applications of finite state machines is language recognition. This application plays a fundamental role in the design and construction of compilers for programming language. section 313.2, we show that a finite state machines with output can be used to recognize a language by giving an output of 1 when the string from the language has been read and 0 otherwise. However, there are other types of finite state machines that are specifically designed for recognizing languages. Instead of producing an output, these machines have final states. A string is recognized if and only if it takes the starting state to one of these final states. So final states with no output, but with some states designated as accepting states, are specifically designed for recognizing languages. So we can, so this gets into the set of strings, the concatenation of A and B, where A and B are subsets of V star, denoted by AB, is a set of all strings of the form XY, where X is a string in A and Y is a string in B. So we have an example. You can feel free to walk through that and get some more insight into that. We can have a finite state automaton. And so it consists of finite states, a finite input alphabet I, a transition function, and assigns a next state to every pair of states and inputs. So that we have this expression, an input or start state as 0, and a subset F of S consists of final or accepting states. One of the things I like to think about this is, say, like a garage door opener, or you go to a store and it has an automatic door opener. It responds to input, and it causes a response within its possible states, and it just continues to operate without giving you a specific answer. It just continues to function with its programming. You can also have language recognition by finite state machines. And so a string X is said to be recognized or accepted by the machine with this kind of setup if it takes the initial state S0 to a final state, that is F of S0X. The language recognized or accepted by M, denoted by LM, is a set of all strings that are recognized by M. Two finite state automata are called equivalent if they recognize the same language. And so this just gives us some details along this, but I'll just keep it at a high level point of view and say we're just trying to see if we recognize a language and we're able to pass on that information. So here we have an example: construct a finite state machines that recognizes the set of bit strings that begin with 2 zeros. And so this is what we're doing. It needs to have these 2 zeros, and then it continues on. So we're just sensing the first 2 digits. Here we have construct a finite state automata that recognizes the set of bit string that contains 2 consecutive zeros. So here's some more things that we can be thinking about here. And I'll just go on from that. We also have a non-deterministic finite state automaton, and FSA, and so it consists with all of these details. So we can represent a non-deterministic finite state automaton using a finite state machine where we give a list of possible next states from a pair of states in an input value. We construct a state diagram, which we're showing here for an example for a deterministic automaton, by including an edge from each state of all possible next states, labeling edges with the input or inputs that lead to that transition. We use the abbreviation NDFSA for that, and DFSA for a deterministic finite state automata when we need to distinguish between the two. So we can find a DFSA equivalent to an NFSA, and I won't go through the details, but this just tells you how we can go from one to another, and I'll just refer you to Rosen to get some more details. So this is an example. Find a DFSA that recognizes the same language as an NFSA. So we have two languages, two different approaches, but they both produce the same result. And thus we can be looking at, well, what other some other criteria? What is its complexity? How well does it perform? But they are equivalent is what we see as a bottom line. So you can walk through these details, and I recommend you see Rosen to get some more information. Okay, let's look at language recognition next. We'll look at regular expression, Kleen's theorem, regular set and regular grammars, and more powerful types of machines. So we have seen that the finite state automata can be used as language recognizers. What sets can be recognized by these machines, although this seems like an extremely difficult problem, there is a simple characterization of the sets that can be recognized by finite state automata. This was first solved in 1956 by the American mathematician Stephen Kleen. We'll get into that. He showed that there is a finite state automaton that recognizes a set, and only if that set can be built up from the null set, the empty string and the singleton strings, by taking concatenation, unions, and clean closures in arbitrary order. Sets that can be built up in this way are called regular sets. Regular grammars were defined in section 13.1. Because of the terminology used, it is not surprising that there is a connection between regular sets, which are the sets recognized by finite state automata, and regular grammars. In particular, a set is regular if and only if it is generated by a regular grammar. Finally, there are sets that cannot be recognized by any finite state automaton. We will get an example of such a set. We will briefly discuss more powerful models of computation, such as push-down automata and Turing machines. Turing machines will what we'll be focusing as we finish up this lecture and this chapter. The regular sets are those that can be formed using the operations of concatenation, union, and cleans closure in arbitrary order, starting with the empty set, the set consisting of the empty string, and singleton sets. We'll see that the regular set are those that can be recognized using the finite state automata. And so to define the regular sets, we first need to define regular expressions. Okay. So here is some information on regular expressions over a set I are defined recursively by this, and each regular expression represents a set of specified by these rules, and sets represented by regular expressions are called regular sets. I'm going to let you look over those in more detail and refer you to Rosen. So here's an example. What are the strings in the regular set specified by their expression here? And so here is the solution to that you can study. In terms of finite state automata, regular sets, and regular grammars, Kleen established the connection between regular sets and sets recognized by a finite state automata. And there is a close connection between the regular grammars and regular sets as well. So I'll just keep that at a high level. And here is Rosen talks about a set not recognized by an FSA. So Rosen shows that a set recognized by a finite state automaton if and only if it is a regular. Rosen also shows that there are sets that are not regular by describing one such set. This is the one that he talks about. The technique used to show this set is not regular illustrates an important method for showing that certain sets are not regular. And so he's given this set, and his goal is he wants to show that that set is not regular. I'm not going to go through all of these details, but using this kind of information and this graphic that Rosen describes, he shows that there's a contradiction and thus it's not regular. And that's sort of a 10-second view of what Rosen is trying to go over there. And you can see that in more detail by going through Rosen. So the main limitation of finite state automata is their finite amount of memory. This has led to the development of more powerful types of machines, push-down automaton, linear bounded automaton, and Turing machines. And this is more powerful than these other ones. And this is what we're going to focus on next. And I'll have the remainder of our time be us looking at this and giving a survey, a high-level understanding of what this is. So we'll give a definition of Turing machines, how we can be using Turing machines to recognize sets, computing functions with Turing machines, look at the Church-Turing thesis, and finally, computational complexity, computability, and decidability. So the finite state automata studied earlier in this chapter cannot be used to deal with general models or of computation. They are limited for what they can do. For example, finite state automata are able to recognize regular sets, but are not able to recognize many easy to describe sets that we can conceive, which computers recognize using memory. We can use finite state automata to compute relatively simple functions, such as the sum of two numbers, but they cannot be used to compute functions that computers can, such as the product of two numbers. To overcome these deficiencies, we can use a more powerful type of machine known as a Turing machine, after Alan Turing, the mathematician and computer scientist who invented them in the 1930s. Basically, a Turing machine consists of a control unit, which at any step is one of finitely many different states, together with a tape divided into cells, which is infinite in both directions. Turing machines have read and write capability on the tape as the control unit moves back and forth along the tape, changing states depending on the tape symbol read. Turing machines are more powerful than finite state machines because they include memory capabilities that finite state machines lack. And we can show how to use Turing machines to recognize sets, including sets that cannot be recognized by finite state machines. And we can also show how to compute functions using Turing machines. Turing machines are the most general models of computation. Essentially, they can do whatever a computer can do. Note that Turing machines are more powerful than real computers, which have finite memory capabilities. So those are just a few thoughts here. This is what a Turing machine can be thought of. And I already mentioned some of these comments here, so I won't read them again. So this is the control unit, and this is the infinite tape. And so if it's an infinite tape, it has infinite memory. And so that's the distinction between what this is like and this abstraction of what a regular computer is able to do with finite memory. So this is the formal definition of a Turing machine. I'm not going to go through this. You can see this in Rosen, or feel free to pause and digest that information. So this just gives you an example of a Turing machine in motion. And so what is the final state when the Turing machine T defined by these 7 tuplets? And so basically it's going to go back and forth depending on what it's called to do. And since this is an infinite tape, it can be winding forward or backward as far as it needs to based on what it's called to do and the amount of computations that's needed to come up with a solution. So we can be using Turing machines to recognize sets. And so this is the strategy of how you can do that. I'm not going to read this whole list. So feel free to pause the video again to be thinking about that. So in section 13.4, we showed that there is no DFA that recognizes the set here. So this is the one that we had over 2 slides that we tried to solve, and we showed it with a contradiction. We will now construct a Turing machine that recognizes a set. So we couldn't do it with a finite state machine, but we can do it with a Turing machine. And so that's going to be the takeaway that I want to leave with you. And this gives some of the specifics of how we would design that Turing machine to accomplish that. We can compute functions with a Turing machine. So we can use to compute the values of a particular function. And then it gives an example of how it could go about doing that capability. This just goes into more details of that, walking through that exercise. The church Turing thesis, the church Turing thesis says that given any problem that can be solved with an effective algorithm, there's a Turing machine that can solve this problem. It's called a thesis rather than a theorem because the concept of solvability by an effective algorithm is informal and imprecise, as opposed to the concept of solvability by a Turing machine, which is formal and precise. We can discuss decidability and complexity. Decision problem asks whether the statement from a particular class of statements are true. Decision problems are also known as yes-no problems. You can see what they talk about giving some more information. When there is an effective algorithm that decides whether the instance of a decision problem are true, we say that this problem is solvable or decidable. However, if no effective algorithm exists for solving a problem, then we say that the problem is unsolvable or undecidable. A function that can be computed by a Turing machine is called computable, and a function that cannot be computed by a Turing machine is called uncomputable. So that just gives a little bit of perspective on that. We've talked a little bit about class P and class NP. In a non-deterministic Turing machine, the restriction that no two transition rules begin with a pair XY is eliminated. Hence, there may be more than one transition rule beginning with each state, tape symbol, pair, so that there may be a choice as to which rule to use at each step. So a non-determinist Turing machine recognizes a string X if and only if there exists some sequence of transitions of T that end in a final state where the machine starts in an initial position with X written on the tape. So we just have some more things about the classes P and NP. I'll just go over some of this. A decision problem is P, the class of polynomials time problems, if it can be solved by deterministic Turing machines in polynomial time in terms of the size of its input. A decision problem is NP, the class non-deterministic polynomial time problems, if it can be solved by non-deterministic Turing machine in polynomial time in terms of the size of its input. Problems P are called traceable, where the problems not in P are called intraceable. So just some more perspective on N and P. And the last chart on that, for a problem to be NP, it is necessary only that there be an NDTM that when given a true statement from the set of statements addressed by the problem can verify its truth in polynomial time by making the correct guess at each step. So there's a lot of information here, and this just gives you a perspective of the what was developed with Turing machines, and still some of this is utilized today as we think about some computing type problems. So the last thing that Rosen wanted to include, and so this is the last chart of this lecture, is wrapping things up with a millennium problem, because every deterministic Turing machine can be considered to be an NDTM, where each state tape symbol pair occurs in exactly one transition rule with this. And so the most famous open question in theoretical computer science, and one of the millennium problems with a $1 million prize, is whether every problem in NP is also P. that is whether P is equal to NP. So I'm going to let you guys think about it, but this is something, if you would like to solve this, you can make $1 million. And that's just one indication that studying computer science and all the things that we have had a chance to be thinking about discrete mathematics and number theory can be profitable. All right, well, thank you very much, and I hope you enjoyed the lecture.